Hello there, Mr. Sutton here, bringing you the Algebra 2 11.1 Part 1 homework solutions on defining and using sequences in series. In this one, we will be focusing on sequences. For the first few problems, they're giving us the nth term expression, a rule for a sequence, and they want the first 6 terms of the sequence. So for all of these, we're basically just taking whatever the rule is and plugging in the numbers 1 through 6, the integers 1 through 6, into that rule. So for A1, we're just doing f of 1, where f is just this 6 minus n business. So I could use Desmos, but I think I can do this one in my head. This is just 6 minus 1, which is 5. And then A2 is 6 minus 2, which is 4. Then we have 6 minus 3 is 3. 6 minus 4 is 2. 6 minus 5 is 1. And A6, that's 6 minus 6, is 0. On this problem, to get the first 6 terms of this sequence, I basically have to plug in the numbers 1 through 6 to this expression here, which I'm going to just refer to as f. So we're just doing f of 1 for a1. That's just going to be negative 1 squared, which is just negative 1. And I'm pretty confident I can do this without Desmos. So we've got now negative 2 squared is negative 4. Negative 3 squared is negative 9. Negative 4 squared is negative 16. Negative 5 squared is negative 25, and finally negative 6 squared is negative 36. For this problem, we're trying to get the first 6 terms of this sequence. You could put this as a function in Desmos and just plug in the numbers 1 through 6 to get that, or you could try doing it in your head. I'm going to do it in my head here. I think I can manage these numbers. So f of 1, that's going to be 2 times 1 over 1 plus 2, which is 2 over 3. For f of 2, we've got 4 over 2 plus 2 is also 4, so that reduces to 1. And then for f of 3, we've got 6 over 5. F of 4, we've got 8 over 6, which reduces to 4/3. For f of 5, we're going to have 10 over 5 plus 2 is 7. And then for f of 6, 2 times 6 is 12. 6 plus 2 is 8. 12 over 8, we can reduce that to 3/2. For this one, we are trying to figure out the next term and also a rule for the nth term of this sequence. Now this one looks a little bit hairy here with these decimals, but let's just not get intimidated. Let's just work through it. So let me first check to see if we're adding the same number each time. So from 4.2 back to 1.2, that's 3. 9.2 minus 4.2 is 5, so we're not adding the same thing every time. Let me look for some other patterns here. So other patterns, we might have perfect squares, so let's check that. We've got 1, 4, 9, 16. Does that kind of correspond with what we're seeing here? Well, these are actually all the perfect squares with just a plus 0.2 added there. This first one is really just 1 squared plus 0.2. 4.2 is really 2 squared plus 0.2. 9.2 is 3 squared plus 0.2. So I think we're seeing the pattern here. The next one after the 16.2, we would need to do 5 squared plus 0.2. That's going to be 25.2. And then for the rule for the nth term of the sequence, we're just going to have n squared plus 0.2. We can write an or f of n equals that. For this problem, we're trying to get the next term and the nth term rule for this sequence here. We got some more decimals going on. So let's go through our list of kind of common things. So one thing we look for is if we're adding or subtracting the same number every time. So from 4.2 to 2.6, that's a difference of negative 1.6. And then we're losing another 1.6 to get to 1, and another 1.6 to get to negative 0.6. So we're definitely decreasing negative 1.6 every time. So that means that we've got some multiple of negative 1.6 going on. So what do we have to change about that to actually get these numbers? Because we don't have negative 1.6, negative 3.2, negative 4.8, or any of those here. So negative 1.6 by itself, if I added that to 5.8, that would get me this 4.2 here. So if I added 5.8 to negative 1.6 times 1. What if I did negative 1.6 times 2 plus 5.8? Well, that would be negative 3.2 plus 5.8, which is 2.6. And then let's put the negative on that. There we go. This would be negative 4.8 plus 5.8, so that would also be 1 there. So then our next term is going to be negative 1.6 times 5 plus 5.8. Or you could simply subtract 1.6 from this fourth term here to get negative 2.2. And then our nth term rule is negative 1.6n plus 5.8. For this one, we're trying to get the next term and an nth term rule for this sequence. So we've got 1, 2, 4, 8. Very clearly we are multiplying by 2 every time. So these are all powers of 2, kind of, sort of. But the first power of 2, if I did 2 to the 1, that would be 2, not 1. And 2 to the 2 would be 4. So we actually need to subtract 1 from our exponent so that we're doing 2 to the 0 on this first one. So if we do 2 to the 1 minus 1, 2 to the 0 would give me 1. 2 to the 2 minus 1 would give me 2 to the 1, which is 2. 2 to the 3 minus 1 would be 2 squared, which is 4, and so on and so forth. So then for the next term after the 8 here, we need 2 to the 5 minus 1, 2 to the 4th, which is 16, which you probably could have just doubled 8 to find that the old-fashioned way. But now we do need an nth term rule. So once we've done this, we can see that we just have to replace this number we keep changing with an n. So then a sub n equals 2 to the n minus 1. To figure out the next term and nth term for this sequence, since we've got some fractions here, and since these don't appear to follow any kind of multiply by the same number or keep adding the same number sort of pattern, I'm going to look at the numerator and denominator separately and see if I can kind of analyze those in isolation. So let's look at the numerator. We've got 2, 4, 6, 8. Well, these are all multiples of 2. So if I have 2 times 1, 2 times 2, 2 times 3, that'll get me those numerators. Now the denominator, we've got basically just adding 1 each time. So if I had 2 plus 1, 2 plus 2, 2 plus 3, 2 plus 4, that would get me my denominators. So again, 2 times 1 and 1 plus 2 gets me my first fraction. 2 times 2 and 2 plus 2 gets me the next one. 2 times 3 and 3 plus 2 gets me the next one. So to get the next term, I need to do 2 times 5 and 5 plus 2. So that ends up being 10 over 7. And then just for the rule, we've got 2 times n over n plus 2. For this table, it's dinner time. We've got some rectangular tables that are placed together along with their short edges as shown here. So we've got 1 table, 2 tables, 3 tables, And we want to write a rule for the number of people who can be seated around n tables, however many that is, arranged in this way. Then they want us to graph the sequence. So let's just sort of count the chairs and see if we can come up with a pattern here. So we've got 4 chairs that can go on each individual table on the sides. So for this first one, we have 4 times just 1 table. Plus we have the 2 at the head and the whatever the other head is of the table. So we've got 4 times 1 plus 2, or 4 plus 2, or 6. So 6 for this first one. And again, this is kind of obvious. You could have just counted this, but we're trying to think of this in terms of patterns and see something that we can write a formula for. So we're writing out a lot of the details here. So for the next configuration, we've got 2 of these tables. So we have 4 seats times 2 tables, plus the 2 at the end of the tables. So that's 8 plus 2, or 10. And then for 3 tables, well, now we have 4 tables times 3, plus the 2 at the head of the table. So that's 14. And then we can keep going in this manner. I think we can generalize at this point that we're going to have 4 times n plus 2. And that'll be our rule for the number of seats at the nth number of tables. So let's go ahead and graph this on Desmos now. Now to graph this, we can't simply do 4n plus 2 because that would be a continuous function. and that would assume that we have like fractions of a table, which we don't. So we need to do these as distinct points, and we're just going to do maybe the first 6 of these. So to do this, let me set up a table, because that's how I can graph distinct points. And then for my x values, that'll be the number of tables. So we got 1, 2, and I'll just auto-complete this out to 6. And then for the y1, I'm going to erase that and put the formula here in terms of x1. So let me just cut and paste the x1. So this is going to be 4 times x1, all of that plus 2. And this gives me these numbers that I had here extended out a little bit further. And if I want, I can do a little zoom fit. And there's what this looks like. So not surprisingly, this is a linear pattern, not a linear function because it's not continuous, but it is a linear pattern. And here's the cut and paste of what I just saw there.